Okay, so we have finished rigid body kinetics, second law, and now we're starting work energy. And so with work energy, what we're going to do is exactly the same thing we did in chapter 3, 4, both of those together. We're going to look at the same equations and then figure out how things go. So I have an object or a mass element dm, which is located a distance r from the center of mass. Center of mass is g, and the distance from g to dm is x bar, y bar, and you have been given an x-axis, a y-axis, and a z-axis. We'll not worry about three dimensions. And we have ij, so we're consistent in terms of direction. Okay, tonk, 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 tonk. Oh, the other thing, 24, 25, 26 lectures are now online, and the OneNote notebook is out. All right. So let's look at a single element. And that, we know, is going to have a kinetic energy of that. So it's a particle. It doesn't have distance associated with it. It doesn't have size associated with it. And so I can take that m sub I and instead write it as 1/2 vi squared dm, and t for the entire object is going to be 1/2 over the mass vi squared dm. Vi, as you've gotten used to now, can be written in terms of the velocity of the center of mass plus the relative velocities. And that's where it gets fun. You get Vgx in the I direction, Vgy in the j direction, and maybe I should write this over here, Vi equals Vg plus Vi relative to g, plus omega k of the object crossed with xi plus yj. And I've written it as, there. So that first part here is this part. The second part here is this part. And so you can see that what you're going to get out of this is a rotational component. So up till now, we haven't really thought too much about rotation, but it's appearing in our energy or our velocity equations. So you can say that Vi equals Vgx minus omega y, Vgy plus omega x in the j direction. So one of the things that, and I'm kind of sort of going towards that same direction, one of the TAs, Coder Jobber, has sort of suggested that instead of sort of writing things as a cross product, you should, if you're looking to make sure you remember things, just write the main formulas out of this so you know you always have an omega minus omega y in the I direction plus omega x in the j direction. So not make it a two-step formula, but a one-step formula. So if you do that, you have Vi, and for kinetic energy, you just do Vi dotted with Vi. And that will be Vgx squared minus 2vgx omega y plus omega squared y squared plus vgy squared plus twice vgy omega x plus omega squared x squared. Okay. All right, so we can sort of separate this out into sort of three parts. We have the translational component, which are just the vgx squared, the vgy squared. We have the rotational component, and we have this last bit right here. And it's omega x and omega y. So we can write that in terms of vi dotted with vi, which equals, and I should write these as vectors, so they are vectors. And you end up with vg squared, so the first term is just vgx squared plus vgy squared, so that's the total velocity. Okay, that's fine. Minus this term plus gy omega x plus omega squared r squared. And just as a reminder, there's r squared right there. So that's the distance. So you have, again, something interesting that's sort of popping out here. You have total energy in terms of translational component velocity, you have a rotational component velocity, and you have this messy term right here, which I don't want to deal with. But I know that t is not equal to just that. It's really 1/2 the integral of vi squared dm. So I can substitute in my expression here, and the integral mvg squared dm minus vgx omega over my dm plus vgy omega integrated over the mass x dm plus 1/2 omega squared, which is constant, integrated over r squared dm. All right, so I have the first term, which is constant. So that vg doesn't change. So it doesn't matter what I do here, it's going to pull right out. So I'm just doing an integration on mass. So I can bring all of that out and bring that directly. So that term there. And when I do that, I end up with 1/2 mvg squared. I have this term over here. And the reason I wrote it in red is because r squared dm, you already know, is I sub g. So it doesn't matter what I do there, it's just going to be there, plus 1/2 ig omega squared. That's how you add in all of the directional components. Now, the last two terms that are left are integrated with respect to the center of mass. So everything on one side of the center of mass is equal to everything on the other side of the center of mass. So if I draw a line, and I have some sort of body like this, and I calculate this area equals that area. So one is positive, one is negative, and all of the terms that are there, because it's about the center of mass, these terms go away. So integrates to 0. I'm just going to add a little bit more. Because this is with respect to the center of mass. So now I know that I have a new term, or I have a new expression. And it's not a surprising expression. You really should be expecting to see something to deal with the rotational energy. And so with the rotational energy, you end up with this final sort of term, and this is the expression you need to know for kinetic energy. So if you're doing everything with respect to the center of mass, you're going to have that expression. So it then, of course, kind of breaks down into a whole bunch of different terms. So first of all, for translation, and I have an object, same thing as before. I have, say, A, B, and G, and the body is moving in, say, some sort of motion, but it's translating. So if I look at that governing equation, or this new equation that I've written, I have T equals 1/2 mvg squared plus 1/2 ig omega squared. For this particular case, omega is 0. And if omega is equal to 0, T equals 1/2 mvg squared. So that's good. Second case is rotation, and you can guess where that's going to go. There, I have, say, an object and it's pinned at a point and has an omega associated with it, and V sub g, that's g, that's 0.0, and that's r sub g. Now, if I do everything about the center of mass, I still have a translational velocity, because this object is both moving with respect to the point here, and it's rotating. So in order to solve that case, T is equal to 1/2 mvg squared plus 1/2 ig omega squared, which is equal to 1/2 m r omega, or rg omega squared plus 1/2 ig omega squared. Because it's a fixed point rotation. If it's a fixed point rotation, the thing is sort of rolling around. Everything is referenced to that point, and I can say that the velocity of g is just going to be velocity of O plus velocity of g with respect to O. And if I do that, then I end up with these two expressions. Now, of course, again, as you're looking at this, 1/2 m, I've substituted Vg with Rg omega, and I squared it, and here it's the same term as before. And that will equal 1/2 times Ig plus mRg squared omega squared, which is, again, the parallel axis there. Go ahead.
Is Ig the moment of inertia of the bar about point G?
Yes, it is. So Ig for any object is the, again, slender rod. So this is going to be 1/12 ml squared, or 1/3 ml squared, L squared for I naught, and Ig in this case. And remember that you're dealing with rotation, or sorry, with standard sort of shapes, and you should be able to pull those things out. But again, sort of as a reminder, And the parallel axis theorem will hold true because in this particular case there is no velocity no translational velocity, no slip at the surface of interest. So that's why you can do that. And you will see this over and over again. So remember that as you're looking at problems where you have something weird happen and you forget or can't figure out what's going on. So in general plane motion, you have, again, an object and v sub g, let's say omega. And as you're looking at these objects, in this particular case, you cannot make any sort of simplifying assumptions. So you're stuck with what you originally started with, which is t equals 1/2 mvg squared plus 1/2 ig omega squared. And so you're really just trying to solve these problems the same sort of way. The main thing to sort of recognize is that you're dealing again with problems that are force, velocity, and distance. So, yeah, if you want instantaneous information, you're looking at second law. If you want sort of information about velocity after an object has traveled the distance, and now that distance can change. Up till now, it's always been linear distances, so 3 meters. Now it could be, 5 rads or something of that nature. So rotation counts as a distance. Work. Okay. Again, force acting over a distance. That hasn't changed. And again, these are scalar properties. They're not vector properties. So they don't depend on direction. And so these problems tend to be a lot more straightforward in terms of approach, but they only give you magnitudes. So if I have something that's sort of traveling over for some distance, s, and it starts at 1, ends up at 2, that object is going to be interesting. But I can also have a different type of motion. I have an object, again, same sort of thing as before, but now it's T1, or, yeah, T2, it's fine. But it goes from theta 1 to theta 2. So it's displaced in a counterclockwise motion, and you're sort of dealing with that, and you end up with angular displacement. So you end up also with work of a couple moment. And that's going to be force times the distance. So again, it's force force R, but here, for example, I have an object. It has a center of mass at G, and excuse me. And you end up with a force that's causing a clockwise moment here. So the force, when you add them up, force times r over 2, force times r over 2, they are going to cause a moment. That moment So if so again, if I have an object that's sort of pushed like this and it just sort of travels, it does no work. This moment doesn't do anything. But if at the same time I have an object and it starts at a position and it gives me a force, and then it rotates around, and I probably should have gone the other way, but I'll put it as F and F. You know, at time 1, time 2, and it displaces d theta, and it is an r over 2. Then it is doing work. So work of a moment is equal to F r over 2 d theta plus F r over 2 d theta. Because again, for now I'm just calling this a positive sort of operation, but here I'm saying clockwise is positive, which I probably shouldn't. But it's rotated through to this position. Now, what that does is it causes work. So dum is F r d theta, and you can write force times the distance as a moment. So as a moment, it's not really usually defined as specifically as a force at position x. It's a moment that's been applied to the object. And if you look at some of the problems you've done in the past looking at angular momentum, you did see problems with moments being added, and we didn't really give you a distance. We just sort of said, okay, they displace over theta. So you end up with an expression that is dum m d theta. So you have all that. You now have a new work term that's appeared, and that work term is going to be important as you look at some of the problems you have. So that's work of a couple moment. So at this point, I have T kinetic energy, which is 1/2 mvg squared plus 1/2 ig omega squared. So I have the kinetic energy of the object, because this is an object that has both size and mass. I'll end up with a translational term and a rotational term. So I also have a problem that I want to deal with as quick as I can. where work is now still going to be springs, gravity, friction, and couple moments. And I've sort of separated these out in terms of what I'll treat as work all the time, and eventually what I'll treat as potential energy. So I don't want to deal with work of a spring. I don't want to deal with work of gravity. And I find that it's hard for me to visualize. So remember, that's sort of where we're going to end up. We should sort of look at some, first of all, kind of obvious one, or first one. So I have point A here. I have force normal. So a force that's being applied to the pinpoint of a revolving body does no work. So that's a normal force. It's sort of sitting there. It's not displacing at all. And the force normal acting on the end of a rod is also going to be a zero work case. So those are that one's kind of obvious. You already know that. You've seen cases where you have rotation or motion on a curved path, and only component of force that acts in the direction of the path actually causes anything to happen. However, this is the hard one. So I have here a wheel, and that wheel is moving from position 1 to position 2. And in the process of moving, I have a force of friction. And in this case, I'm going to also sort of define this as rolling without slip. With your eyes, you obviously see that the friction force has moved. But the point of contact with the floor has a velocity of 0, which means the friction force can't move. And so this is something, when you have rolling without slip, you have no displacement of that friction force because it cannot displace because it's at 0 velocity. And I am going to skip entirely talking about work more than I have to, and start to say, hey, my equation is this. And that's my conservative form of the work energy equation. And here, annoyingly, I have conservative and non-conservative force. You can guess where this is going. So I would like to go back to what I had in the previous chapters, chapter 3, and sort of say, hey, I know that if I stretch a spring and return it to its initial state, there's no hysteresis. The course is great. There's nothing happening to things. Gravity is good. It just goes up, it comes back down, everything goes back to 0. So my preferred form of this is going to be now, this caused a lot of problems when I kind of I have a lot of questions on Piazza about this one. So they say, well, these are two different equations. How can you, mix up work and all of this stuff? So one thing to remember, and this is sort of an aside, is that if I have T1 plus V1 minus V2 of G plus V1 minus V2 of E plus all of the work done from non-conservative forces, it equals T2, hey, it's work 1 to 2 of conservative forces. Don't double count, clearly. Don't put gravitational work and do gravitational potential. But if you really, really, really want to have work in your expressions, write it as a potential and then come back and get your work out. But all of these are exactly the same. They don't change the equation, they don't change anything. They're just different ways of dealing with the terms in the equation. Same thing as before, all I do is I define a datum. Doesn't matter how I define the datum. Often I will choose a datum that's either at the top or bottom of the motion, but here I've chosen one arbitrarily in between. It will still work. And this is a distance y, and it makes my life a lot easier. So if I'm dealing with work, and say, for example, I had a problem with work from 1 to 2, and this is position 1, and this is position 2, I could say V1 is going to be mgy, V2 is negative mgy, and I'll know I'll have 2 mgy. On the other hand, if I go the other way, 1 here to 2, I'll end up with minus mgy, and minus 2 mgy. What's important is not sort of calculating work, it's avoiding calculating work. You also have the standard expressions . And here, I have a spring. And with the spring, I'll either say stretch it or compress it by distance s. And in the process of doing that, I'll sort of define compressed, stretched, and in all of these cases, I end up with V equals 1/2 ks squared. Now I still have the same problem. The force, when I stretch it out, wants to pull it back in. When I push it back in, the force wants to push it back out. But in these cases, the potential energy is just the amount of compression, how much the spring has been stretched or compressed. So in this course, you have potential energy, and if you solve things in terms of potential energy, you'll often find it's a lot easier to deal with than dealing with the work expression. So you can always write anything any way you want to, but if you have non-conservative forces to deal with, it becomes a form of kinetic plus potential plus work 1 to 2 equals final kinetic plus final potential. Or if there are no non-conservative forces in the problem, then all you're looking at is the work. Or sorry, all you're looking at is the potential. Questions? We're going to cover, so there's 2.25 lectures left on this. So next week I will finish all of this on Wednesday. Yes, Wednesday. Now, a very typical case that you look at are things that are moving in sort of ducts or channels. So I have mass A and mass B. They're both massless. Rod A, B has a mass M. And anything else I want to say about it? It's released from rest. What is omega at some arbitrary angle theta? So if you release a system like this from rest, you know that VB is going to be, or B is going to move downward. It's not going to move upwards, please. So VB is down. VA is going to be, in that case, in order for the rod to remain rigid and stay in place, VA will be moving to the left. And so if VA is moving to the left, this is one of those few cases where, hey, it's really good to use the instantaneous center of zero velocity. And you use the instantaneous center of zero velocity just to figure out what direction and what the rotation is. So for example here, you can just sort of say, hey, that's going to be the rotation. I know that because I can look at those 2 points. I also can drop the perpendiculars and pull out that information from it. So for a problem like this, you do T1 plus V1 equals T2 plus V2. And I'm going to make my life a little bit easier and say that everything is happening at the top. So in that case, T1 is 0 because it starts from rest, and V1, or gravitational potential, which is the only thing that's playing a role, is 0 to start. And then it's going to end up at some arbitrary position in between. So the datum's at the top. There's no springs, there's no friction, and there's not much else to say there. Everything is referenced with respect to the center of mass. Now, I don't know what that velocity is, but I know that the center of mass is here. So that's g. I can figure that out. And so velocity of g is just going to be omega times L over 2, because at that instant, it's rotating about that instantaneous center. So I end up with L over 2 omega quantity squared plus 1/2 Ig omega squared. All right, so okay, so that's my kinetic energy. So this is going to be 1/2 m times L squared, I'm going to jump ahead, 1/3 omega squared. And I know that because, again, it's an instantaneous center of zero velocity. That instantaneous center of zero velocity is going to be, what is IG again? Of the rod. Or what about the two masses? Yeah, I said they were negligible. They were zero mass. But one of the things to remember is that zero mass means zero moment of inertia, which is correct. And so you have 1/12 ml squared for the rod. And if you add 1/12 plus 1/4, you end up with this 1/3. And again, this is something that you know from pinpoints of how to do the shifting with moments of inertia. Vg is equal to minus 1/2 mgl sine theta. And that's just, the weight has dropped a certain amount. It's half of, probably shouldn't write it like that. That's better. Same thing. Minus mgh, it's dropped by L/2 sine theta. So T1 plus V1 equals T2 plus V2. 0 equals 1/2 ml squared over 3 omega squared minus 1/2, I don't want to do that, mgl over 2 sine theta. And if you then substitute in terms, you end up with omega equals 3g over L sine theta, all to the 1/2. And that kind of makes unit sense too. So it's kind of a form that you've already seen before, but you've got meters per second squared here, you've got meters here, so meters and meters cancel, so it's 1/second squared square rooted, so it's 1/seconds, which is rads per second. The magic of rads. And so as you're sort of doing that, you immediately get an answer, and that's your result. Questions? Go ahead. Oh, because we have to follow this right here. So we don't care. So this is going to be rotating at one velocity, whatever that is. Actually, it's these. This is not a great drawing, but these distances are all the same. But L/2 is the distance to that point. So it's L/2 at that position. Okay, this is geometry. And it's rotating about there. Ooh, okay. So things that get me in trouble. All right, so again, I'm going to talk about power. I recognize, and I know that people always ask, but it's not covered in the course, but it's important for, I think it's important for you to know, and I put it in my notes in the vain hope that one year I will be allowed to teach power in this course. Power is important because you need to understand what you're paying for and what you're getting out. And so power is the rate of doing work, and it's force dotted with velocity. But if you remember, that was the one we were used to. You also can say, Ugh. That is not looking better. There we go. You can also say you can introduce the idea that there is power associated with moments. So work done by a moment, md theta, dt. If it's a constant moment, which we usually consider, d theta dt. So if it's d theta dt, that's omega, which is the angular velocity of the system. Again, we don't cover it in the course. I think it's still useful for you to know and to be familiar with. Questions? All right. All right. I'm going to start this, and I know I won't be able to finish it, but it's a nice problem to start with, and it's something that if you have time, you can actually do it on your own just to convince yourself that you can handle these sorts of things. I have a 25 kilo bar, which is this right here, rotating downwards at 2 rads per second. And it's not shown here. What the implication is that it's rotating like this, which kind of makes sense. The spring has an unstretched length of 0.45 meters and a spring constant of 180 newtons per meter. You're given an initial sort of distance from a ball that will travel with the spring. And all that ball does is allow you, a wheel, to sort of keep the spring vertical. So if you start at a position at position 1, it's like this. Ball then moves at position 2 over like this. But it just maintains the vertical orientation of that spring. Force, velocity, and distance. So bar is rotating 2 rads per second. Distance is associated with angular displacement. The spring has an unstretched length of 0.45 meters and a spring constant of 180 newtons per meter. To what angle measured from the horizontal does the bar rotate before it stops? Force, velocity, distance. Okay. All right. Theta. It's just a little weird because of that. Now, again, I really shouldn't do this, and as I update things, I'll update these. But for this particular problem, it's a lot easier for me to look at it from the perspective of a clockwise positive rotation. So I'm doing scalar operations, and those scalar operations are going to continue through. Okay. O is the position where the pin is, right there. I am not going to derive this anymore, but that 1/3 is just a parallel axis theorem with 1/12 ml squared. So I'm switching from the center of mass to the point of interest. V1 is 1/2 K, and I'll call this L1 minus L unstretched quantity squared. T2 is 0 because it's coming to a rest. And in 5 seconds, V2